And everybody's happy place is different. It's strange, yeah. I almost can't even differentiate whether that was a dream or whether it really happened.
Stoked. You guys are probably too old to remember this type of stuff. The Roku watch. Schuber X. Pew Pew multiplayer mode.
Hi, my name is Philippe, and I'm a developer here at Flipboard, your personal magazine.
Flipboard. Pet driving cars. In the kitchen with Hannibal. Yeah, so that's April Fool's Day. What time is it?
In today's world, our lives revolve around two things: connectivity and portability. But we're constrained by traditional power sources. Wall sockets, chargers, even solar energy simply aren't flexible enough. At Sony, our challenge was to come up with a power source that could go with you anywhere without compromising your daily routine. And we've done it. Introducing Sony Power Foods. Now the same fuel we've used to power ourselves for thousands of years can be used to power personal electronics. Our engineers and culinary technicians have come up with a way to tap into the amazing energy of food. We've formulated an enzyme that enables the chemical energy of organic matter to be transferred directly into gadgets. We're bringing about the next step in electronic evolution. We've created voltaic enzyme. This vital component converts the energy stored in fats and sugars into a usable source of voltage for any device, all while enhancing the taste of our favorite food, even a freshly grilled hot dog. And Sony Power Foods aren't just for techies and foodies. Everyone will love the tasty variety of charging options. No outlet? No worries. Try a bite of Crunchy Loops, and you'll be charged by the amazing taste in every spoonful. The same simple sugars that Crunchy Loops breaks down into energy provides the exciting flavor that we all crave in our morning cereal. But we didn't just stop with cereal. We knew we needed to power even the most active lifestyle. Sony's Protein Energy Bar is the perfect companion for fitness and outdoor enthusiasts. Each bar contains a daily serving of fiber, protein, and charged lithium. So now you can plug in, chow down, and feel recharged to take on the day. There's nothing more special than celebrating those important moments in life, such as birthdays, anniversaries, and graduations. And there's nothing more frustrating than being stranded without power when we need it most. Sony's delicious Power Food Cake Mix provides voltage to your electronics in 3 sumptuous flavors: vanilla, red velvet, and classic chocolate. Now you can be sure you'll get a shot of the cake you're photographing because it comes with a full electrical charge. It even provides extra energy to the candles. With Sony Power Food, you'll never have to interrupt a special moment again to plug in. You simply eat up. The Sony Power Food line. now available at Sony stores and groceries near you.
Yeah, there's a ton of these. As much as I'd like to watch more the rest of the class. All right, the last one before the break. Let's do this. You guys have a break, right? 2 weeks? Woo. You guys are spoiled. I didn't have a 2-week break when I went to. I did this yesterday. This is the first time ever that you've noticed that the slides are like a day behind. Like this date just automatically fills in itself. So I was doing this yesterday. So whatever. Yeah, they're American slides. Yeah. Did I spell something wrong? Anyways, okay, so today we're going to cover the dot product, projections, and cross product, which are operations on vectors. So let's look. So is it possible to multiply two vectors so that their product is a useful quantity? So remember, when we are looking at number fields that we've defined, we also have to define the operations that go over them. So it's really up to us to define one so that it's useful. Okay, so we have this dot product, which is also called the scalar product of two vectors, because it's an operation which takes two vectors and returns to you a scalar. So if we have two vectors, A from A naught through AN, and B from B naught through BN, the dot product is denoted A dot B. This is why I was hesitant to use a dot for multiplication before. And it's given by this sum. Basically, A naught times B naught plus A1 times B1 all the way through AN times BN. So we can write it like this, or equivalently we can write it in this form. So A dot B is the sum from I from naught to N of AI BI. So you should note that this dot product is a function with domain Rn cross Rn, that is pairs of numbers from, nope, that's wrong. Who's taking notes again? Oh no, wait, this is right. This is right. Sorry. Yeah, you take a vector of length n and another vector of length n, and it maps to a scalar. Right? This is why it's sometimes called the scalar product. Okay, so what's this? 2. What's this one? Well, it's minus 6 plus 14, which is what? 8? Minus 2, 6. Cool. What about this one? Think again. So remember that these I, j, and k's will turn it into a vector, right? So this is 1 times 0, 0, plus 2 times 2, which is 4, plus minus 3. So it should be 1. Oh, yeah, minus 7. Okay. At least it's right on the slides. Okay, so what kind of properties do the dot product admit? So if A, B, and C are vectors in Rn, and C is a scalar, then all of these properties hold. A dot A is the magnitude of A squared. A dot B is B dot A, which we recognize as commutativity. A dot B plus C is A dot B plus A dot C, which is what we recognize as distributivity. CA dot B is equal to C A dot B is equal to A dot CB, which is like an associativity of scalar multiplication over dot product. And 0 dot A is 0 for any selection of A. So we have a 0 for the dot product. Yeah, you guys don't really have to write this down, right? I post the notes and slides. Okay, so let's do a proof of the first one. That is A dot A is the magnitude of A squared. So A dot A is A naught squared plus A1 squared all the way through AN squared, which by definition is the magnitude of A squared. That was an easy one. proof of 3, which is A dot B plus C is equal to A dot B plus A dot C. So we have A dot B plus C is equal to this, which is basically its definition, A naught through AN dot B naught plus C naught all the way through BN plus CN. If we distribute out like this, so you get A naught times B naught plus C naught all the way through AN times BN plus CN. We can distribute that out and regroup, which by definition is A dot B plus A dot C. So most of these proofs on dot products and cross products are going to be very routine.
Why is there dots in between the A naught, B naught, and A naught, C naught?
Where here?
And the next dots.
These dots?
On the same line.
Here.
Yeah, in the middle there.
Oh, there should be a plus here.
And then the next one. In between them.
This?
Yeah, why is it dots?
Should there not be dots? Yeah, there shouldn't be dots there. And there should be a plus here. Thank you. Huh? Like, yeah, these dots shouldn't be here. Yeah.
April Fools.
Yeah, American April Fools. Okay, so for your physicists, this is this dot product is defined a little bit differently. So this theorem is used as definition in that discipline. So if theta is the angle between A and B, which is displayed here, then A dot B is equal to the magnitude of A times the magnitude of B, or maybe we can say the length of A times the length of B cos theta. Okay, here's a proof. So using the laws of cosines, we have this. Right, so if this is A, this is B, this is A minus B, then the law of cosines say that the square of this length plus the square of this length minus twice the product of the lengths cos theta is equal to this length squared. Right? So observe this still works if theta equals 0, that is if the two vectors are lying on top of one another, or theta equals pi, that is the vectors are pointing in opposite directions. Or when the vectors themselves have 0 length. So this is really, this proof works in all cases. Well, let's finish. So using properties 1, 2, and 3 of the dot product, we have A minus B squared. The length of that is A minus B dot product A minus B, which is A dot A minus A dot B minus B dot A plus B dot A. Yes, B dot B. It's another one. So you get length of A squared minus 2AB plus length of B squared, which is equal to the length of A squared plus the length of B squared minus 2 length A, length B cos theta. Right? So we have this is equal to this from the last slide, which gives this statement, which implies this, which implies that. Yes, this minus shouldn't be there. Right? But the point is we have A dot B is equal to the length of A, length of B cos theta. Right? So this is a very useful way of moving between geometry and algebra, right? Which is something that we do a lot with these type of quantities. You get that one as well? But this should be a minus. Yeah. Okay, if vectors A and B have lengths 4 and 6 with the angle pi thirds between them, what is A dot B? Right, so it should be, we use this equation. So the length of A is 4, the length of B is, well, not 5, it's 6. Let's see what I worked it out to be. Yeah, so that should have been a 6, not a 5. Okay. Right, so I can give you instead lengths and angles, and you can still calculate the dot product. That's the point I'm trying to make. Corollary. So a corollary is a simple deduction, or like a deduction that's immediate from a theorem or proposition. So from that theorem, we can deduce that cos theta is equal to A dot B over the length of A times the length of B. So which is a good way of determining the angle between two vectors, right? If you're given the vectors themselves. All right, you can calculate cos theta with that simple formula, right? So if we have a vector 2, 1 and a vector 3, 1, and I ask what's the angle between them, we have the length of A is the square root of 2 squared plus 1 squared, which is root 5, and the length of B is 1 squared plus 3 squared, which is 10. And using that last formula, after realizing the dot product is 2 times 1 plus 1 times 3, which is 5, it follows from the corollary that cos theta is equal to 1 over root 2, and thus theta is equal to arc cos 1 over root 2. Right, so if I give you two vectors, which you assume have tail at the origin, then you can calculate the angle between them by 4. Let's do another one. What is the angle between 2, 2 minus 1 and 5 minus 3, 2? So the length of A is 2 squared plus 2 squared minus 1 squared, which is 4 plus 4. Yeah, 4 plus 4 plus 1 is 3. It's 9. Square root of that is 3. And the next one is 25 plus 9 plus 4, which is 38. A dot B is what? (10 minus 6 minus 2), which is 2. So it follows from the corollary that cos theta is equal to 2 over 3 root 38, and thus theta is the arc cos of 2/3 1 over root 38. So have you guys ever worked with orthogonality or perpendicularity? Okay, so what does it mean for two things to be perpendicular? Right, so as I say up there, two vectors A and B are called orthogonal. Have you heard that word before? Okay, if the angle between them is pi over 2. Right, so what can we deduce from this? Well, using that corollary, we know that cos pi over 2 is what? 0, right? So A dot B is 0 if and only if A is perpendicular to B. Right? Let's take a look at this. A dot B is equal to 0. That means the length of A times the length of B cos theta is equal to 0, which means arc cos theta is equal to 0, which is only the case when theta equals pi over 2. Right? Or something that's equivalent to pi over 2. Here's a question. Let's show that 2i plus 2j minus k is perpendicular to 5i minus 4j plus 2k. Right? So that's the vector 2, 2 minus 1 and 5 minus 4, 2. So we should expect that this dot product is equal to 0. Good. 2 times 5 is 10, minus 2 minus 8 is 2, minus 2 is 0. Great. And thereby the vectors are perpendicular. So this is an easy testing question. Right? Are the following vectors perpendicular? Right? Calculate one dot product.
Can it be the next test?
Huh?
Can it be the next test?
Sure. Will you get it wrong? If I put this question on your next midterm and you get it wrong, I'm going to be furious. Okay, so notice that when cos theta is greater than 0, when theta is in the range 0 to strictly less than pi half. And cos theta is less than 0 when theta is strictly greater than pi half to pi, and 0 otherwise. Right, so geometrically, we can think of the dot product as a measure of the extent to which two vectors are pointing in the same direction. So notice that when the two vectors are the same, the dot product is square the length of the vector. Right? So at most, we're going to be able to get the square of the length of the vector. But in general, the dot product is positive when theta is acute. Right? And it'll get bigger and bigger and bigger as theta gets smaller and smaller and smaller. Right? When A and B are perpendicular, that is, they're not pointing in the same direction as little as possible, when theta is pi half, and when the dot product is positive, this means that theta is obtuse. Right? So in some way, this is a measure of how these vectors are pointing. Right? Okay, so something I gave on the last tutorial.
A times B is positive for both of these.
Oh, that should be negative. Yeah, less than 0. So I spend so much time drawing those figures. I don't look at the thing underneath them. Okay, so in the last tutorial, I gave you a question that discussed unit vectors. So a unit vector is just a vector which is, has length 1, right? Has unit length. And any vector can be made to be a unit vector just by dividing it through by its length. These are useful because it's a standard way of talking about the direction of a vector. Right? If we just want to know where something's pointing, we typically just talk about its unit vector because things get a lot easier if the length of the vector you're working with is 1. Okay, so I say that because I would like to talk about the vector projection. That is, if you give me two vectors and I want to take, have you ever guys done projections? No, okay. So the vector projection of B onto A is denoted the projection of B onto A, and is the vector given by A dot B over the length of A, right? The length of this projection is given by A dot B over A, right? This is a scalar, and it's pointing in the direction of A. Okay, so this may not be that meaningful, but this picture certainly is. So it is the shortest distance. The projection is the shortest. The projection is given by the vector, which goes from the common heads of B and A, and is the shortest distance from the tail of B to A. You can think of it as like firing a beam of light perpendicular to the thing that you're projecting into, and looking at its shadow, right? So just note that the projection in the end will be a vector, right? This is a vector. The projection can go in the opposite direction of the thing if you're projecting to, if what you're projecting is in the opposite direction of the thing you're going onto, right? So just keep that in mind. The scalar projection of B onto A is also called the component of B along A, and it's simply the length of the projection. Right? So there's nothing new here. Right? We project B onto A, and the component is just this length, right? Which we can calculate as the length of B cos theta. That should give this length. Right? So the projection itself can just be given as the component of B onto A in the direction of A. Right? And this follows directly from the definition. Okay. What is the scalar projection of B onto A? Well, first we want to calculate the component of B onto A, which is defined to be this, right? Which is minus 2 plus 3 plus 2 over the length of A, which is 4 plus 9 plus 1. So it's 3 over root 14. Okay. That's the scalar projection, or the component. Okay. What is the vector projection of B onto A? Well, I picked them deliberately to be the same. So to get the projection, we just take the component of B onto A and multiply by the direction of A. So we know that the component of B on A is 3 over root 14. And the unitization of A is the vector divided through by its length, right? So 4 plus 9 plus 1 is 14. So we have 3 over root 14 times minus 2, 3, 1 over root 14, which gives you this vector. Right? So the projection of B onto A is going to be this vector. Right? Another. Yeah, sorry, yeah, I removed it too. So another easy midterm question. Yeah, my end of the midterm is going to be like so easy compared to the other side. Have you guys done any of those Maple TA questions yet?
Yeah.
Great. How about the rest of you? I'm going to put more. I'm going to put some vector questions. Just make sure to do them over your break, because you do have a midterm, like when you come back, yeah, or whatever you guys call it, a quiz or mid-semester evaluation. Or why don't you call it assignments? Why do you call them assessments? Okay, I take that back. That makes more sense. We call them assignments. Yeah, and then assessed. It's weird. Such a backwards country. Okay, so here's another application of the dot product.
Isn't your country the backwards country because you're one day behind us?
That is true. Huh? You are from the future. But then why do we have all the better tech? Tony Abbott, okay. Damn those liberals. He's a liberal, right? Your liberals are conservatives. It's weird. Okay, anyways. So here's another application of the dot product. So if you have a force and you want to move something some distance or displacement, we can calculate the work that is done using the dot product. Right, so I think I have an example. Yeah, so if we have a wagon, so imagine this is a wagon. Like I connect a wagon here. And this is the handle of the wagon. And this is the angle at which you're holding the wagon's handle. And you pull that wagon through this displacement. Right? So what is the work done pulling a wagon 100 meters along a horizontal path with 70 newtons of force when the angle of the wagon's handle is pi4? Well, the work is going to be the 70 newtons of force times 100 meters cos pi quarters, which is equal to 3,500 root 2. And since we're in physics, it is appropriate to calculate a decimal. What's this? Aha. You guys are smart. Yes, so we get 4,949.75 joules of work to pull this wagon. And so, believe it or not, this was the stopping point for this lecture that I was given. Right? So I'm going to do the So I'm going to do the next lecture after that, since I've already accomplished the first 2-hour lecture in the first half hour. Anyways, and I doubled the amount of examples too. Okay, so the vector product is the next operation on vectors that we have. So given two non-zero vectors A and B, what is the vector C which is perpendicular to both of those vectors? Any ideas of how we could calculate this? Yeah, but so geometrically you'd be correct, but I've spent some time developing algebraic means of talking about these things. So how can we use the algebra? Yeah.
Could you just multiply A and C and multiply B and C, which value C next to this one?
Yes. Okay. So we need to solve A dot C is B dot C is equal to 0. That should be equal to 0. Where's my correction, man? Equal to 0. Right? So the first equation is A naught C naught plus A1 C1 plus A naught C2. That should be 0. And simultaneously, we should have B naught C naught plus B1 C1 plus B naught B2 C2 is 0 as well. So do you guys know how to solve equations like this? Like systematically? Okay, so you'd know how to do it by, say, using a pivot like this.
Well, we can call it that, but we don't have I know how to do it, but...
So what would you do to solve these equations then? Huh? Panic. Because it's underdetermined, right? Well, I know you know how to do it, because you just said so. But it's underdetermined, right? We have 6 variables in 2 equations, right? So after we finish these this vector stuff, we're going to move into linear algebra, where I'm going to show you a systematic way of solving these things by using pivoting. Okay, but normally what we want to do is eliminate one of the variables, right? So the first thing that we have to take stock of is what is the thing we're solving for and what is given? Yes?
We're solving for C naught, C1, and C2.
Yes.
We're given the A1, A naught, A1, A2, and B naught, B1, and B2.
Yes. Okay, right. So you should not see these A's and B's as variables. They're constants. Right? They're stuff that you've been given. Right? And these C naughts are the free ones. Right? So the game is, I give you A and B, and you have to give me back C. Right? So in the end, we should have equations for C as functions of A and B. Right? But that's fine. OK, so these are called pivots. Right? We'll learn why later. So if we multiply the second equation by 2 and the first equation by A2, we can eliminate C2. Right? Because this is A2, C2, and this is B2, C2. So if I multiply this one by B2, we're going to get A2, B2, C2 minus A2, B2, C2. Because these two things are equal to 0, so I'm free to either add or subtract them. Right? Because 0 minus 0 is still going to be 0. Right? We could have made this plus, and then I could have just multiplied by minus a squared if I wanted to. Right? Right, so if we work this out, I highlighted the things that will cancel in red. And then that will disappear, and we're left with only C0 and C1. Right? But is equal to 0. So notice the form of this. Right? Yeah, what should we do now? How can we finish this? Hmm? OK, so suppose we move this, then what? Well, we want this to be 0, right? So notice that we just ignore what's in the brackets here. We have something. This equation really has the form P times C0 plus Q times C1, right? This has an obvious solution. If we want this to be equal to 0, if C0 is Q, this should be a minus. If C0 is Q and C1 is P, we're going to get PQ minus QP. Right? So that's going to be equal to 0. So the answer should be, I set C0 to be the second thing and C1 to be the first thing. Right? Then their difference is going to be 0. I may have screwed up the signs here a bit, but I'll fix them. Right? So thus, C0 is this, A1, B2 minus A2, B1. And C1 is this, A2, B0 minus A0, B2. Is that right? Oh, yeah. This is reversed because I took a minus.
And the C0 is should equal to
C0.
notice 4 has form blah, 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 which is obviously C0 equals
Nope, C0 should be Q. You're right. And C1 should be P. Right. Thank you. OK, so if we find these values, we can just go back. Whatever. We can just go back and substitute C0 and C1 into either of those two equations, right? Thus eliminating every variable except for C2, and then solve for C2. Right? So here's the solution. Given A and B, the vector which is perpendicular to both A and B has these components. Right? The first one, the second one, and the third one. So our conclusion. The vector C perpendicular to both A and B is given by this. Right? A1, B2 minus A2, B1, A2, B0 minus A0, B2, and A0, B1 minus A1, B1. Okay? This is interesting in itself. Right? But it's going to be exciting to start solving these linear equations in like arbitrary variables. Right? The field of linear algebra and system solving like that is like extremely robust. Like the entire field of numerical analysis is basically the study of how to solve these linear systems. Right? It is hugely useful. OK, so why am I telling you this? Well, this operation that we sort of gave for exactly two vectors is called the cross product or vector product. Right? So we showed how we could take two vectors and take the dot product of them to get a scalar. Right? So that was the scalar product. We can also take two vectors and define an operation on them which gives you back a vector. OK, first of all, these should be vector brackets. But did I screw something up in here? The last one?
Yep.
A0, B1, A1. Yes, that should be a not. Good eye. Good eye. Huh? OK, so basically, we're going to define the vector product as the vector that's perpendicular to the two vectors that you're given me. So what is the vector perpendicular to I and j? Ah, yes, it's k. But thank God, right, that you used your geometric intuition. Right? Sometimes, if I ask you a complicated algebraic question, thinking about it like geometrically is going to be the easier way of doing it. You could have skipped all these steps if you really wanted to. But how did you know it was in the positive direction? There are two vectors which are perpendicular to I and j. There could be another one pointing down. Well, we'll find out. Right? But if that was true, what would that indicate about the cross product? Not commutative. Right? So this is important to understand. See, you guys were so scared when I defined all these terms, but it makes it so easy now to talk about these things. Okay, so actually this cross product was discovered by Hamilton, like in his search to generalize C to higher dimensions. So recall that we talked about the quaternions, and they had the form this, right? So we had a quaternion which had a scalar part A, and this part, bi plus cj plus dk, which he called the vector part. Right? That's where sort of these terminologies for vectors come from. Also recall we had these identities. I squared is equal to j squared is equal to k squared is equal to ijk is equal to minus 1. And let us multiply these two quaternions, and let us multiply two quaternions with zero scalar part, right? So let's remove the scalar part and multiply two quaternions and see what happens. By the way, I gave you a tutorial question where I asked you to take the cube of a quaternion. That was exactly the question I was asked 3 times. So as long as you do a reduction at each step, it should be fine, right? Because if you square it, the thing that you're going to get back is only going to, once you simplify, should only have, again, 4 terms. And then you should square that. So if you squared it first and got 16 terms, and then multiplied it by 4 to get 32 and reduced, that was not the smart way of doing it. Right? You want to reduce it every step, because then you're only ever multiplying 4 terms by 4 terms. So my answer to that is yes. Although it was kind of a dick move for me to give you that question. Okay, so keeping that in mind, let's multiply these two quaternions out. Right, so we just distribute everything. So bi squared f and b gij. Well, whatever. You get the point. We distribute it out, and we find this. We have this scalar part and this vector part, and the interesting thing about it is the fact that this is the dot product of these two vectors, and this is the cross product of these two vectors. So we could define arithmetic on quaternions, or specifically multiplication on quaternions, as a vector operation which maps two vectors with a scalar part to a dot product and a cross product. So that's quite interesting. So this is how these naturally fall out of Hamilton's work. There's a better way of remembering these operations. Have you seen the determinant? Okay. Who else has seen the determinant? Oh, okay, great. So you know what matrices are, or matrices. Okay, for those of you who don't, it's just a way of organizing numbers. Right? So we just have a box. It has 4 positions, so 1, 2, 3, 4. Right? When I put bars around this box, it defines an operation called the determinant, and it's given by this. So the way to remember this is it's this diagonal minus this diagonal. Right? So AD minus BC. There is another determinant of order 3, which is for a 3 by 3 one, and it works out to this. So have you guys know the trick for 3 by 3 determinants? Okay. So look at these constants out here, right? A0, A1, A2. First notice that the signs alternate. This is plus, this is minus, this is plus. Okay, so what is the thing that we multiply A0 by? So you go to A0 here, and you strike out this column and this row. And what's left is the thing that you're taking the determinant of. Right? So if we strike out A0, this column and this row, we're left with B1, B2, C1, C2, which is this. Right? The second one is a minus, remember, because we're always alternating. So we strike out the column for which A1 is in and the row for which A1 is in. And we're left with B0, C2, B2, C0.
So wouldn't that also mean that you could have plus A1 and have B2, C2 to start and then B0, C0?
Sorry, you want to expand along this row?
Well, for the A1, you can have it positive and you do for B2 before you put B0 in the matrix.
I'm not sure I follow.
Yeah. So when we've done this before, or years ago, you imagined that there was another column and you just wrapped around. And so then you could do it with all positives.
Oh. Yeah, I've never done it that way. But if someone else in the class agrees with you, I'm going to say, sure. This is the way I was taught. There's a lot of equivalent forms. Maybe the one of the equivalent forms that I'm going to give soon is what you're talking about. But in any case, this is the way that I like doing it. And so the last one, this A2, is strike out this column in this row, and you're left with B0, B1, C0, C1. Right? And this is, in fact, how the determinants are defined. Right? So this is our base case. We know how to take the determinant of a 2-by-2 matrix. These are called cofactors. Right? And this is called the cofactor expansion. Right? So in the similar way which I showed you how to do this expansion, we could have a 4-by-4 matrix and go A0 and multiply it by the 3-by-3 matrix that's left over. And then that 3-by-3 matrix determinant can be determined like this. Right? So we keep going down and down and down and down. I'm not allowed to show you the determinant this semester. Apparently it's something that you're going to learn about in part 2 of this course. And hopefully I prepared you well enough for it. OK, so if we finish this, oh, well, I didn't expand all of these, but this would be A0, B1, C2 minus B2, C1, and so on. OK, so what's the determinant of this?
7.
If that's 7, man, I'm going to be perfect in this course. So let's see. OK, so it's 1 times 0, 2, 1, 4. What's the next one going to be? Minus 2 times. Great. And then the last. OK. OK. So we have minus 4. I don't think you're getting perfect. Minus 4, minus 2, plus 12. 38. That's a multiple, is it? No, it's not. Just trying to help you out. OK, so another easy midterm question. Take the determinant of this matrix. Maybe I'll even give you the exact same one. Or maybe I'll give you one that equals 7. So just remember. Which one? OK, so I feel there's some confusion. Is it negative 18?
Yeah.
Minus 4.
That should be
So I copied this out of a book.
yeah, that should be 6 plus 5.
6. Yes, this should be a plus. Because it's 6 minus minus 5. OK, so we have minus 4, minus 22, minus 26, minus 12 is minus 38. OK. So I'm going to, OK. Determinants will be 7 or 38. OK? There you go. So if you don't get those 2 values on your midterm, you can't hedge your bets. This is a math test. You'd be surprised how many people do that, though. When I was teaching calculus in Vancouver, many students would do the question twice, hoping one of them is right. So this was really something that we had to discuss. How should we mark this question? Given 2 solutions, what? You think it's the first? That's what I would do, right? I did first. Someone else said you should take the average of the 2. Because that would guarantee you could at most get half the marks, right? So that person wanted to punish the student for doing something so silly. Huh? It's just funny to think that they think they could hedge their marks or hedge their bets. We did true-false questions once, and I remember one person got 10 true-false answers incorrect. I felt so bad. I almost wanted to like give them bonus marks for, because you'd almost need to know the correct answers to do something like that, right? And deliberately guess wrong, because like how like that's 1 over 0.5 to the 10 probability of getting all the questions wrong at random, which is like ludicrously small. Huh? No, 2 to the power of 10 is way more than 1,000. 2 to the 10 is, oh, maybe you're right. Yeah.
2 to the 10 is 1,024.
Yes. Okay, so it's way more than 1,000, like 24 times more. It's still pretty spectacular, right? That probability. Okay, so here are some alternate forms of the cross product using some algebra. You guys seriously can't work out this probability? Okay. Here's what's the probability of getting 1 true-false question correct? What's the probability of getting 2? But do you see that you multiply the probabilities?
Yeah.
Right? There are 4 different selections of true-false, right? True-true, false-false, true-false, false-true. One of those four configurations is true, right? If you do go to the 3, there are 8 possible ways of choosing. One of those is the true one. Have you guys ever heard of the Monte Carlo problem? Or the Monty-Hall problem?
Yeah.
So who hasn't? Has anyone in here not heard of the Monty-Hall problem? Okay. So you're on a game show. I have tons of time, so I can. Okay, so you go on a game show and there's 3 doors, right? Okay, but let's discuss how this solves. Okay, there's a car behind one of the doors, and there's goats behind the remaining 2 doors. So this is how the game plays. I say, okay, who's going to be the contestant? Yeah, because you take all the corrections, so he deserves it. Okay, there's 3 doors. Actually, do I have markers? Of course I don't. So I will use this. No, there's not. I'm supposed to bring them, but I never do. What the? Okay, so there's a car behind one of these doors. So which door do you pick? 3. You're supposed to like turn around to the audience. You guys have the prices right here? You won't get it. Okay, so you pick 3. Okay. So I say, okay, you pick 3. I'm going to tell you that behind door number 1 is a goat. I don't know. Yeah, it's a devil baby. Fine, behind door number 1 is a devil baby. So I saved you from that fate. Okay, would you like to switch doors?
Yeah.
Huh? You have a good feeling about even? Okay, so you do know that switching the doors is the correct solution. But who can explain to me why in a simple way?
2 out of 3.
4 to 7.
Because on your first choice, you had double the chance of getting a goat than you had of getting a car.
Yeah.
And then you took out a goat.
So a lot of people...
But goats are more reliable than cars.
A goat has at least 1 goat power, right? Depends on the car. Yeah. Okay, so listen. there are two strategies that you can employ in this problem, right? You can either try and pick right immediately and not switch, or pick wrong and switch, right? What's the better strategy? Well, to pick right, you have a 1 in 3 chance, and to pick wrong, you have a 2 in 3 chance. So obviously, it's the second option which is better. This is very perplexing to people. But the reason this is the case is because I, the host, is introducing new information that is contingent upon your choice. Right? So embedded in this problem is a conditional probability. Right? When you choose a door, that eliminates it from the doors that I'm able to open. Right? So you'd be surprised how vicious of an argument you can have with someone about the merits of this problem.
The best we found with the solution actually is death threats.
Really?
Yeah. She received death threats from like other professors and whatnot for the solution.
Can't throw a word out there.
But like the solution, it seems to me, is like so clear. Mythbusters did this too, and they proved that. Well, proved they empirically verified this.
If you read Wikipedia on that one problem, the discussion went on for decades. It was quite heated.
You just listen out, people go. So this is 20 minutes that we've been through, so 25 minutes. What's all this? Next lesson.
This is 4 hours of lecture, and I'm almost done. Hmm? You want a break? Do you guys want a break? Because I don't think there's much left. Oh wait, no, there's heaps left. Okay, okay, go take a break. 10 minutes. Yeah. Oh, okay. Okay. Well, you know I post the slides in the notes. Okay. Oh, yeah. Okay, so you guys want another probability question? No, I'm not going to tell the answer, but you can try to work it out. How many people do you have to have in a room in order for the probability?
Yeah, it is.
Prove that if you have 23 people in a room, that the probability of 2 people having the same birthday is greater than 1/2.
Amazingly low.
Prove. Well, it's because it's an extraordinarily high number of parents. But yeah, you can prove that. Give you bonus marks. Wait, we can just look it up on the internet. Scrap that. Okay, if you can come to my office and explain to me it in a reasonable manner after having researched or determining it yourself. Oh, you just like forward to it. No, you have to explain it to me like on the board. No.
3 words.
I don't understand.
It's really cool.
Is there just
Don't.
No, I'll count contractions as 1 word. But it's a very interesting result, right? There's very neat things in probabilities. If I want to learn more about these things, buy my textbook. Or just give me a nickel. About the same to me. I sold 6,000 textbooks. I make $600. It's like the worst, it's the best way to make not a lot of money extremely slowly. It's a stochastic process. I'll show you a little bit what they are when we start doing it. It's like the mathematics that you need to study, like the stock market, valuation. Like imagine you put a mouse in a box, and this box is broken up into compartments, say 6 of them, and then there's like doors between some of the boxes. So at every step, the mouse has like. Oh, maybe I can drop this. Sorry, bud. So it's like this, right? You have a mouse. So this mouse has to move from here to here, right? But then once it's here, it has a 1/2 chance of moving back, or a 1/2 chance of moving here. So the type of math that you need, so the type of questions we want to ask on this is, say after a million steps, what's the chance of the mouse being here? After an infinite amount of steps, what's the proportion of time spent in each box? Huh? Or if...
Because let's go through the first door and the second door. The third door just leads to you.
Oh, well, okay, sure. Maybe I need to do this, right? Or like if I open this to the outside, what happens?
How long?
Like on average, how long does it take for the mouse to escape?
2 seconds.
Depends on the intelligence of the mouse, right?
Cross over with game theory, is that what you're...
No, not really. This crosses over with linear algebra, surprisingly. I can set this up as a matrix, and then like what's called the probability matrix. It's a matrix whose elements sum to 1, right? And then if we take powers of this matrix, we can determine some of these things. And if you take the power to the limit, then it gives you the distribution of the time spent in each of these things. Yeah, I'll talk about it a little, since like I have so much extra time. Oh, I don't know what its application. I know it's useful in Brownian motion, for instance. Yeah. Any follow-up questions? I can move these around, right?
Minotaurs somewhere.
Ah, Minotaur.
It's got to be somewhere. Centaur. No, double.
You can bring up the NT across the C, E, and then put the AU after that. Then you can make MI and E and O can go above the TA, then have UR. And then you've got UR. Put the Griffin in. Yeah, Griffin.
No, but that's
You can make Kraken out of the K-R.
Kraken.
Release the Kraken.
Yeah, you got the A and Griffin. If it's not Griffin Act, it's Griffin. You just move the AK in, yeah. Yeah, and that to the other side. Yeah.
Then you got Pegasus.
Unicorn.
See?
Ooh.
Yeah, it's true, actually. Oh, it's Pegasus.
Unicorn.
Unicorns are so weird, right? There's nothing girly about a horse. There's nothing girly about a knife. But you like put those two things together and you get a unicorn.
But the P comes the E in Centaur. Yeah, so it was one. It is Pegasus. I told you it was Pegasus.
We have Pegasus?
I thought it was Pegasus. I know, and then you look put the P above the E. Yeah.
Pega.
Yes. Winner, chicken dinner.
All right, wasn't that fun?
Looks like it.
You want one more?
Yeah.
Then I seriously have to do some math. Oh, hidden clue.
What?
Start with this. No, it's snake.
Snake?
Is it types of snakes though?
No, it's only class level.
No, that was the general theme. Mystery word.
No, it's Bonza.
Try moving the ILF to the left of the
which one is path 2 or path 4?
Don't look up the solutions.
Oh, I'm not. I promise.
ILF to the left of the top left. What was it called again? ILF move to DER.
Oh man, we suck. Bonza. Yeah. Can we make Viper? If it's Viper, then it's definitely snakes. How do you spell Viper? I can't make it then. V. You can't, right?
That piece just moving the ILF, put it up on the right, and then the PE.
You don't know this.
PE down the
Bring the
bottom,
T H above the IE.
and the R. RG.
Yeah.
Yeah, that piece you just moved.
Yeah, but like.
Bring the T H above the IE, and you got the VE under it. The VE. There you go, now you started.
Steel?
Yeah, now you get it.
What about burglary?
Oh, what about plunder?
Come on, man, stop cheating.
Yeah, you can actually make fun of it. Yeah, put the
ALUNDER.
No more from you.
Actually, if we're doing that, you're ILF below the P in plunder. You can also
Pilfer.
Move to be above Q. Then RD under U.
Berg. Girl.
Oh, because they're all doing words.
They're all what?
Doing words.
Oh, it's stealing words. Pinch. Nick. Nick. Boom. Bonza! Okay, now we really have to do math.
There's a math one coming up in two sessions.
What? I get to that.
There's 3D geometry on Bonza. You just got to win one more and you get 3D geometry.
I'm going to do more math, right? Okay, so we were talking about the cross product before we took a break. So here's an alternate form, right? We can always use these I, J, and Ks to express things which end up being vectors, right? So A cross B can be written like this, using these I, J, and Ks, which means that we can really pack this in to a determinant that looks like this, right? So is this closer to the form that you were talking about? No?
No, if you swap the columns in the middle matrix, the determinant,
Oh,
you wouldn't need them right.
I see. I see. Yeah, but when you go bigger, it kind of screws things up, right? Because then if you swap columns, if you're doing like a 4x4, then you have to account for that at the step up. But that is a neat trick. Okay, so if we have A is 1, 3, 4, and B is 2, 7, minus 5, then I can calculate this determinant to define the cross product. Right? So we have 3, 4, 7, minus 5, right? So I strike this out and strike this out. Then I have minus J 1, minus 5, 4, 2, and k, 1, 7, 3, 2. Right? So that all works out to minus 43i minus 13j plus k. Right? This is 7 minus 6. Okay, proposition. For any vector A cross A is 0. Why is that intuitive?
Because you can't have a vector that's perpendicular to, well, you have two vectors that are pointing in the same direction, so it doesn't make sense to really say what is the vector that is perpendicular to both vectors.
No, this is saying A is always perpendicular with itself.
No, that's the cross product.
Oh yeah, wait a second. Right. Yeah, so there is no vector that's perpendicular to both those things. Or I guess to make things work out algebraically sensible.
It's A0 times A1, take away A1 times A0.
Each one of those determinants.
Yeah. So there's the proof of that. Okay, sure. I guess this is just a property we're going to define in order to have the cross product be well defined. Yeah, sorry about that. I was thinking of dot product. Anyway, so we define it like this, but in fact it does just fall out of the definition. Because I guess otherwise there'd be an infinite amount of things perpendicular to A. Right? If you have a vector in space, it's like basically any vector is perpendicular to it. Like you can go all the way around it. Okay, so here's a theorem. For any vectors A, B in R3, A cross B is always perpendicular to A, and A cross B is always perpendicular to B. This statement is a tautology. It is always correct. So here's a proof. We're just going to pick the first one because the proof is exactly the same for the second. So A cross B dot A is this determinant times A naught times this determinant times A1 plus this determinant times A2. And if we work it out and expand, we get 0. Right? So these proofs are always very routine. Another theorem. If theta is in the range 0 to pi, and theta is the angle between A and B, then the area of this parallelogram is given by the length of A cross B, which is an interesting result. So consider that we know that the length of A cross B is this AB sine theta. Right? So B sine theta is this height. And we can just take the area of a parallelogram by moving this triangle here and getting a rectangle. So once we have that rectangle, we know that the area of the rectangle is this height times this space. Right? So that's how we get A times B sine theta. Right? Height times width. Right? But since we have this equality, we can just do it directly from the cross product. Right? So this is interesting, that the length of the cross product is equal to the parallelogram that A and B form. Proof. So we're going to square everything just to get rid of all the square roots in the lengths. So if we work this out, you'll eventually get here. Right? There's a lot of intermediate sort of algebraic nonsensory. But you'll find eventually that you can deduce it to this. So once we get here, we can use the properties of the dot product in order to get this, which we'll prove, which simplifies to this, which simplifies to that, and we're done. Right? So in the end, we found that A cross B squared is equal to A squared, length of A squared, length of B squared, sine squared theta. And thereby, the length of A cross B is equal to the length of A times the length of B sine theta. We just have to take square roots on either side of this. Find the vector perpendicular to the plane that passes through the points 1, 4, 6, minus 2, 5, negative 1, and 1, negative 1, 1. Do you know what a plane is? Yeah.
It's a set of, it's a flat 2D surface embedded in a 3D space.
All 2D surfaces are flat.
Well, no, but I mean like flat. Like a sphere is flat and it's a 2D surface.
No, a sphere is a 3D surface. A circle is a 2D surface. and a circle is flat, right? I think the word you're looking for is straight.
Is a pancake flat? Would you consider a pancake flat?
Now we're getting a little bit philosophical here.
3D.
Because it has a height, right? No object in 2D have height, right? A line doesn't have a height. A circle doesn't have a height. Anyways, if you look at a line is straight in 2D, right? So a plane in 2D is a line. A plane in 3D is a surface given by two lines, right? So if I'm in 3D and I say you can go this way and this way, the points which you can get to from there will define a plane. Right? It's like putting a piece of paper in 3D, which can go in all these directions. Right? So if you have a piece of paper, just draw two lines in this piece of paper, and you can define any plane that you want. Right? So analogous to a line in 2 space being uniquely defined by 2 points. Right? If I'm in the plane, I give you 2 points, you run a line through them. Right? This is a unique description of a line. In 3 spaces, if I give you 3 points, this will uniquely define a plane, right? 3 points give you 2 vectors, and these 2 vectors will span a plane. We'll learn more about this when we hit the linear algebra part. More mathematically, planes and spaces are given by equations which are linear. And that is if we use a set of variables and we never employ something like a square or a cube, then we'll always get a plane, right? So the equation for a line in 2D is y plus mx plus b, right? No squares. An equation for a plane in 3 space is ax plus by plus z plus d, right? And that will describe a plane. So the point I'm trying to make is that these 3 points define a plane. So how can we find a vector that's perpendicular to this plane? Yes?
Well, the vectors from P to Q is on the plane, and the vector from P to R is on the plane. So if you had a vector that's perpendicular to both those vectors, then it would be perpendicular to the plane.
Yes. So how do I find a vector that's perpendicular to both of them? Yes. Right. So we need only find a vector perpendicular to this vector and this vector, making sure that the heads of both of these things are the same. Right? You don't want to take the cross product of 2 things like this. Right? We're always assuming that they're meeting. So how do we get PQ? Let's see if you remember what we were taught from last lesson.
You subtract each component of P from the Q. So
Okay.
it would be -2 minus 1, 5 minus 4, minus 1 minus 6.
So -3, 1, minus 7. What about the next one? Oh my god, did I do this right? 1 minus 1 is 0. Minus 1 minus 4 is minus 5?
Yeah.
You were looking at
Which one did I do here?
You repeated the same one. You've written the same
Oh.
one.
Yeah, that's weird. So that's wrong. Right?
What should it be?
It should be
0.
0 minus 5 minus 5. Yeah, what I put in here. So at least that's right. Okay, so the vector that's perpendicular to both of those vectors is given by this determinant, which if you work out gives you this. So the vector that's perpendicular to this plane is minus 40, minus 15, plus 15. Right? Maybe I'll draw you guys a picture of how that looks like. I keep turning this off instead of on. Okay, so we have 2 vectors like this, right? You will see that it defines a plane, right? In this space. Maybe we have some z-axis like this. Okay? And what we found is another vector. So if this is u and this is v, we found a vector that goes like this, right? Which is perpendicular to both of these points. Isn't that neat? Oh, okay, well, I don't hide the answer on this for some other reason. But we can also use this to find the area of the triangle that passes through these points. Right? So you have a triangle that's defined by 3 points in 3 space, and we want the area of that. Well, we know that the cross product calculates the area of the trapezoid, or the parallelogram, that passes through those. And so the area of the triangle is going to be half of that of the parallelogram. Right, so in the last slide, we calculated the cross product of this. So the area of the parallelogram formed by PQ and PR is the length of the cross product, which ends up being 5 root 82. So the area of the triangle is half of this. Right? So again, tons of easy midterm questions. This stuff is very routine. Okay, so another proposition. A cross B is the vector. A and B is the vector perpendicular to both A and B, whose direction is determined by the right-hand rule, whose magnitude, pop, pop, is length of A, length of B, sine theta. So this is how physicists define the cross product, right? So we did it algebraically, but the cross product is also uniquely given by a length and a direction, right? All vectors are given uniquely by a length and a direction. So this is how you can tell which way the vector is pointing, and maybe I'll boot this up again by turning it off. Have you? Okay, so yeah. Okay, so here's the right-hand rule. Take your right hand, and you want to put your thumb in the direction. You want to put your hand so that it curls from A to B. Right? If you're taking A cross B, you want to make it so that this flappy part of your hand is describing the angle, right? And then your thumb is going to point in the direction that the vector is going, right? Because remember, when we calculate magnitudes, it's unsigned. It doesn't. We just know the length, right? So you still, in the end, need to calculate the direction of the vector, because the vector could be going this way, right? If we wanted to do B cross A, right, you'd have to do this, right, to describe that angle. So therefore, you're pointing downward. Right? So if you ever see someone in an exam like doing this, you know what they're doing. Okay, so this is how physicists define it. Ask them why. Okay, so here's a corollary, which again is just a simple result that we can get immediately from a theorem. So two non-zero vectors A and B are parallel, denoted A parallel B, when their cross product is 0. So A cross B is 0 if and only if A and B are parallel. Right, because if you have two lines lying on top of one another, there's no vector which is perpendicular to both. So here's the proof. Two non-zero vectors A and B are parallel only when the angle between them is 0 or pi, and in either case, sine theta is 0. Right, so we know that A cross B is length of A, length of B, sine theta. So that's 0 in both cases, and therefore A cross B is 0. This should be a bold 0, by the way. It's a vector. Right, because we've defined the 0 vector as the unique vector such that it has 0 magnitude. Is the cross product commutative? Give me an example. Well, here's this. Always give the simplest example that you can if I ever ask for a counterexample. No, right? Consider I and J. If you do I cross J, that's this. And if you do J cross I, it's this. Right? So it's not commutative. But it's sort of commutative if you account for the signs. Is the cross product associative? Associative means that we can move the brackets, right? So multiplication is associative because A times B times C is the same thing as A times B times C. No. So I once said that any operation worth its weight in salt, worth its, what is that expression? Worth its weight in salt. In gold. Where I come from, salt is really expensive. So that's clearly not the case for this one, right? But vector spaces are kind of weird in that way. No, something cross itself is always 0. Yeah. So yeah, here's your proof, right? So what's perpendicular to I cross j? That's k. What's perpendicular to I cross k? It's minus j. And you should recognize these as the rules of quaternions, by the way. That's how they fall out. Whereas if we switch the brackets, we're going to get a 0, and that zeroes out everything, right? So here's a simple example of why it's not associative. So here's our first example, really, of an operation which is not associative. Interesting in itself. Okay, here are a bunch of properties that we have on the cross product, dot product, and scalars. A cross B is equal to minus B cross A. So it's not commutative, but kind of is. If C is a scalar, we have CA cross B is CA cross B is A cross CB. That's sort of like a distribution property. We have A cross B plus C is A cross B plus A cross C. Kind of like distribution. We have A plus B cross C is A cross C plus B cross C. Also like distribution. We have A dot B cross C is A cross B dot C. And we have A cross B cross C is equal to A dot CB minus A dot BC. So notice there are no crosses here, because A dot C is a scalar and A dot B is a scalar. Right? So this is a vector sum of two vectors which have been scaled. Right? So you should try and prove some of these. Okay, this quantity here is important. It's called the scalar triple product. Right? So the product A dot B cross C is called the triple scalar product of the vectors A and B and C. Right? And it's given by this determinant. Right? You can work it out. Okay, so just like the cross product was giving us the area of a parallelogram, the scalar triple product is giving us the volume of the parallel pipette. Right? That's what this object is called. Parallel pipette. So we have three vectors, A, B, and C. A cross B gives you, well, okay, how did they describe it here? Okay, so you have B cross C gives you the area of this volume, and then you want to multiply by the height. The area of this parallelogram, the area of that surface. And then you want to multiply the area of that surface by the height of this parallel pipette, which is this h. So that the height is going to end up being A cos theta, right? That's what this length is going to be. And this vector is B cross C. Right? So it turns out we can work it out so that B cross C, the length of B cross C times A times cos theta is equal to A dot B cross C absolute value. Right? So the volume of a parallel pipette given by three vectors is equal to this quantity. Right? I don't know why I drew this so high. This really should have stopped. This is the vector B cross C. Oh, I forgot to put a pause. Okay, so I suppose do you know what coplanar? Do you know what it means for things to be coplanar with one another?
It is in the same plane.
Okay. Yeah, I guess I can't really explain it beyond that. So if you have two vectors, it describes a plane, as we discussed. And this is in the third dimension. So there's another option for the third vector that I described. Either the vector I described lies in that plane that are described by the first two vectors, or it fires itself out. Right? So if three vectors are coplanar, that means one of them can be written as a scalar multiple of the other two. You did this in the tutorial. So if I give you three vectors in 3 space, how can you prove that they're coplanar using this result? If these three vectors lie in the same plane, what should the volume of this? Not 0. No, if C is 0, then we have, oh wait, maybe you're right. Yeah, you're right, sorry. Yeah, Yeah, so we want to show that the volume of the parallel pipette is 0 if these three vectors are coplanar, right? So if we want to show these vectors are coplanar, that is, they're all in the same plane, which will be extremely important later on, we simply just have to show that the triple scalar triple product is equal to 0. And we can easily do that, right? So B cross C is given by this determinant, which works out to this. But we also have to do this dot product, and I gave a formula before, so it's equal to 0. Right? So thereby the volume of this parallel pipette is 0, and this can only be the case when A, B, and C are coplanar. OK, the last thing is an application before we leave. For your physicists, this cross product defines a torque. You know what torque is? If you have a wrench and a bolt, right, you're applying a force to the wrench downward like this. And a force that you apply downward on the wrench is going to get translated to a torque, which is the thing that's unscrewing the bolt, right? So that force, that torque, is the cross product of how you're pushing down on the wrench and the other wrench. So the wrench is one vector. The force you're applying to the end of that wrench is the other vector. And the torque is the cross product, is the vector that's coming out of it, right? So the interesting thing about this is the longer your wrench is, the more torque you're going to get, right? So try and unbolt something with like a tiny wrench versus unbolting it with like a hugely long wrench. Right? So have a nice break. Study. I'll see you guys when you get back. Right? Huh? I did. Yeah, I have been every week. Huh? For these notes? No, I'll put them up. I need to correct them first, right? Yeah. They'll be up before the end of the day. Yeah. We can, but there's new tutorials. Well, I'm going to put up some Maple TA questions. Yeah. Yeah, I can draft together some tutorial questions for practice. I can't give you answers, though. You could come by our offices, I guess. Your exam's going to be extremely straightforward, at least my end of it. It's going to be calculate the determinant of this, calculate the cross product of this, what is the volume of this parallel pipette, stuff like that. And I'll give you a formula sheet. I hate the idea that you guys have to memorize anything. Thank you kindly.
Is the dot product associated?
I owe you a goat.
A goat. Can I have a goat? Is the dot product associated?
Yes. Yeah. Because the things that it's operating on is multiplication and addition, and both of those things are. Yeah.
So you're going to be here in the holidays in case we
Yeah. We don't get a holiday like you do.
Like the Monty Hall problem, there's another one called the Prisoner's Dilemma.
Yeah, that's a game theory one.
Yeah, I was watching a video on that the other day. It's pretty cool.
Do you watch Number File at all?
I did watch some videos, yeah, and Visa also saw that one.
Yeah, he's a nice guy. He's an Aussie, that Number File guy.
Okay, yeah.
Oh, yeah.
So was there bonus marks involved in the
Yeah, have a good
the 23
holiday.
people question? Because I've got all the working out just there.
Okay, go ahead and explain it to me on the board.
On the board, I don't. Okay. Well, so you got 23.
I'm not giving you bonus marks for something that you looked up online.
I know.
It's an interesting problem, though.
Yeah, it wasn't bad. The solutions to your game were all there, like every single section.
Yeah, but like that takes all the fun out of it.
You should have been sitting there still now going, what's this X mean? What are we doing?
Yeah, we would have. Then you wouldn't have had to learn what vectors were, or cross products.
I have a question.
Yes.
Is it possible? Does the cross product generalize to higher dimensions?
Yeah, but they're called Lie groups, and they're kind of complicated and really messy.
Spell that for me.
LIE.
No.
Yeah.
Okay. Maybe I'll.
They're called tensors.
Okay.
Yeah, and they get really. I hate tensors, and a lot of other mathematicians hate working with tensors in Lie groups too.
Okay.
Because they get like super complicated, the arithmetic.
Fair enough.
Yeah, but you can take a look at them. Yeah.
Okay. When are they covered in?
Oh, you won't cover them until like your final years, if you cover them at all.
Okay.
Are you in the math stream or the physics stream?
I'm not sure. I'm doing computer science.
Oh. That's what I did as an undergrad. I'm not sure you'll ever cover Lie groups then, unless you deliberately take courses in math, which I'd recommend anyways. Take as many math courses as you can.
Okay, thanks for that.
No problem.
I have a question. Is there a textbook for algebra?
If you find James Stewart's early transcendentals, yeah, that's what I've been working out of.
Because I can't bring my laptop every day.
Yeah, so find James Stewart early transcendentals. I'm sure the library has this on reserve.
So it's about algebra that we are learning.
Yeah, so yeah, there's a whole section on linear algebra. There's only an appendix on complex numbers.
Oh.
Yeah, there's not much. Like these examples I'm taking straight from that book.
Oh, okay.
They'll have a little bit more of explanation, I guess. There's like some words in between. But do you know what book I'm talking about, or do you want me to write it down?
Oh, yeah. Oh. Oh, this guy also has a calculus book.
That's the book I'm talking about.
So there is calculus and algebra for him, right?
That book, which is the calculus book, has a whole chapter on linear algebra.
And the calculus and linear algebra.
Yeah.
Okay. Thank you.
He was my teacher back at home.
Oh.
Yep.